Hello everyone. So what we're going to do in this video is we're going to look at another law, and this law in electronics is called Kirchoffs law. Now, I'm going to say Kirchoffs laws because there's actually two of them, okay? And they're called Kirchoffs' first law and Kirchoffs' second law. So his first law is in parallel circuits. And remember, parallel circuits is where you have multiple paths for current to flow. So you've got a node, and then the current into that node has the opportunity, so you've got current getting into the node, yeah? And at that node it splits, some current goes that way and some current goes that way. Kirchoffs' first law says the currents coming out of that node must add up to the currents that go into that node. Okay, so you could think of this as being I1. Let's zoom in on that a wee bit, make it a wee bit easier to see. Yoink. Think of that as being I1. You could think of this one as being I2. You could think of this one as being I3. So Kirchoffs' law says that I1 will equal, in this case, I2 plus I3. Okay, there's another way to think about this, and that's if you've got a complete circuit, there's a parallel branch here, 3 resistors in it, and that goes back to supply. Conventional current flow coming out here, coming round towards the node, yeah, call that IT. We'll split at this node, some will go this way, some will go this way, and some will go that way. So that current into the node splits in 3. That current will continue through here and then recombine at the node and then become that full circuit current again. So it'll be IT on this side as well, yeah. These 3 currents in here will be individual currents, I1, I2, I3. Doesn't really matter what you call them, just as long as you give them names. So it could be seen here that IT equals I1 plus I2 plus I3. What we could say is that the current through all of those resistors, so the currents through resistors adds up to the current from supply in this case. Current that's coming out of the battery splits, some goes that way, some goes that way, some goes that way. And the decision, or not the decision, but the size of I1 versus I2 versus I3, even though you know the 3 of them add up to IT, the individual sizes on them will be dictated by the resistances in their paths. So if you've got a really large resistance here, that's R1 and that's really, really large, and R3 is really, really small, then large resistances will choke off the current. So I1 will be really small. If R1's massive, I1 will be small. If R3's tiny, I3 will be big. And if R2 is in the Goldilocks zone, medium, then I2 will be medium, yeah? So that's what dictates the sizes of the individual currents, is the size of the resistance, and we'll get to the point of calculating them as well. So there's Kirchoffs' first law in a parallel branch. Whatever current is going into that parallel branch splits and recombines at the node. Okay, so you can see that the currents through those resistances will be different if the resistances are different. If those 3 resistances are exactly the same value, then those 3 currents will be the same value, and there'll be a third of IT because there's 3 paths. His second law is in series circuits. So remember, in series circuits there only is one path. Yeah. And in series circuits we're talking about voltages. So what we would say is whatever voltage appears across this resistance could be different from the voltage that appears across that one, could be the same, could be different from the voltage that appears across that one. When you put things in series with each other, the voltages will all be different. And what we're saying is that those voltages all add up. So you can find the voltage right across a series, just get another identifier. You can find the total voltage across a series network by adding up all the individual voltages. What that means is, obviously, if one of those three was missing but you knew V4, you'd always be able to work out the missing voltage. So in this case, V4 equals V1 plus V2 plus V3, right? If you put that into a full circuit with a power supply, just put 2, get lazy, 2 resistances. Yeah, that power supply has a voltage, and then whatever voltages you measure across these 2 resistances, going off squinty, don't know why, V1 and V2. So Vs equals V1 plus V2 in that instance. All the individual voltage drops, this is the kind of terminology you would use, okay, so voltage drops in circuit add up to voltage supply. And again, the voltage across this resistive element is dictated by the size of the resistor, but it's the other way around this time. So there's R1 and R2. If R1 and R2 had the same resistance value, V1 and V2 would be the same, and in this case they would be a half of Vs, because there's only 2 of them. If R1 was much bigger, V1 would be bigger. Okay, that's the opposite in terms of resistances and currents. So if that resistance is big, that current will be small in a parallel circuit. In a series circuit, if that resistance is big, that voltage will be big. Okay. In a series circuit, all the series elements develop their own voltage, but the current through them will always be the same. Whatever current is passing here, will be the same current through each of those devices. It's a series circuit. Whereas up here, the current splits, but the voltages across them must all be the same. Whatever voltage is across R1 will be the same as the voltage across R3, because they're in parallel with each other. So you can see how parallel and series circuits, they share the same attributes, but everything's reversed. Okay, so it's currents that change in a parallel circuit, whereas it's voltages that changes in a series circuit. You add the currents up to find the total current in a parallel circuit, you add the voltages up to find the total voltage in a series circuit. Currents will be larger if resistances are smaller. You know, the arrangement is reciprocal in a parallel circuit, but it's the same way round in a series circuit. If the resistances are big, the voltages will be big. So you can see that the relationship changes them, but the type of relationship is opposite. So that's Kirchoffs' first law, is about parallel circuits. Kirchoffs' second law is about series circuits. Let me see if I can come up with some questions on this. Give me a second. Right, okay, so here's a bunch of questions for you. So just state the laws. What type of circuit is this? Can you recognise it? What is the current through R2? I'll refer to the content in the video for the answer to that. And then these three are just testing your ability to recognise that Kirchoffs' second law is V1 plus V2 must equal Vs, that these add up to that one. These 2 questions are the same, they're just asked slightly differently. Do you recognise that those 3 voltages should add up to that one? Calculate the missing voltage supply. Sorry, that's the same deal. This one here, which voltage drop will be bigger, V1 or V2? So you're looking at the size of the resistances to get the answer to that, and again refer to the content of the video for that stuff. Put the voltage drops in order of size smallest first. So which of these three, V1, V2, or V3, what one's smallest, what one's the next biggest, what one's the next biggest, and again, you're looking at the size of the resistances here. In this one, you'll get a wee bit of calculation to do, but it should be relatively easy. V1 and V2, what will they be? What will they actually equal? What will V1 and V2 equal? When you don't know, you know what the supply is, but you don't know what either of those, but you do know the resistance values, and look at the resistance values. And again, I've given you the hint. There's another second worksheet. I've just realised the question numbers will be wrong on this. I'll need to fix the question numbers on this one. But again, it's the same deal, except it's a different type of circuit. Okay, so you've got the two laws, the two different types of circuit. Can you distinguish between them in every instance and apply that law correctly? I'll fix these questions and put it up. Cheers.